Welcome. This is Motion Graphs video number 3. In this one we're going to look at the velocity versus time graphs in relation to a new one, the acceleration versus time graph. Remember, in the last video, video number 2, we looked at position versus time and velocity versus time. But there are 3 types of motion graphs: position, velocity, and acceleration versus time. We mentioned also in the last video that each one of those graphs is like another equally true perspective of a particular situation. So we can have one scenario, for instance, a car moving in the positive direction at a constant speed, and we can do a graph that is position versus time, velocity versus time, and acceleration versus time for that scenario. All those graphs should agree and tell us a different story about that scenario. Let's take a look at that very scenario. Let's say that we have a car moving at constant speed in one direction. Let's make our position versus time graph right here. I need to label it PVT. It's going to be in the horizontal direction, so I'm going to use X to represent the position, and the position is on the Y-axis, so the X symbol is on the Y-axis. T is time on the X-axis. I'm going to have a velocity versus time over here. That's going to be my V to symbolize velocity as a function of time t. And now we need one more graph over here for our acceleration versus time. And our acceleration versus time graph we're going to title as AvT. And I'm going to have my lowercase a on the y-axis, because y-axis is going to represent acceleration, and time again on the x. Time is always on the x-axis with these. Okay, now we have our 3 graphs: position, velocity, and acceleration. What's our scenario? Car moving in one direction, positive, at a constant speed. Let's say we're starting to look at it at the origin. At x equals 0 is the beginning of our little observation here. So therefore I will place my starting point right here at the origin on position versus time, car moving at a constant speed. Remember we said that the slope on the position versus time graph is the velocity. So if my slope on position time is constant, that means my velocity is constant. I'm not speeding up, I'm not slowing down, I'm not changing direction. Alright, what's that look like? On the velocity versus time graph, we're traveling at a constant speed in one direction. We have a constant velocity value. Slope on position versus time is constant, therefore the velocity is a constant value represented on the y-axis of the velocity versus time graph. That number right there on the y-axis, that's going to be the car's velocity, constant. It's in the first quadrant where y is positive, y-axis is positive, so velocity is positive, given that this line is in the first quadrant. Look back over, like we mentioned before, my slope here is constant on the position versus time graph, and that slope is equivalent to the velocity. It's not changing. So we got a linear position versus time graph because we're traveling at a constant velocity in one direction. Linear position versus time graph means we're going to have a flat, horizontal, slope equals 0 velocity versus time graph. Look at our velocity versus time. Velocity is not changing. What quantity describes velocity and how it changes with time? Acceleration tells us how velocity is changing with time. So I look at my velocity versus time graph. Is it changing? Is the value of the velocity changing? No, it's constant. It's a flat line. So that means my acceleration is going to be 0. So if I draw that, which you need to draw an acceleration versus time graph. These graphs are part of your visual component. If the acceleration is 0, you actually need to draw a line right here like I'm doing on acceleration is 0. Make it, just make it a thicker line, or you can just be like, you can do this. If it's 0, you can just add right there. A is 0. I wrote the graph, Mr. Stacy. So acceleration is 0 if the velocity is constant. Before in the last video we talked about how the slope of our position versus time graph told us the velocity value. Well, check out velocity versus time. The slope on the velocity versus time graph, which is 0 in this example, tells us the acceleration. It tells us exactly what the acceleration should be. In our course, acceleration is always going to be either 0 or some constant non-zero value. We don't deal with changing accelerations. Okay, so there's our first example there. Remember we also mentioned in the last video that besides looking at slope and whatever the numbers are on the x or y axes, we can also look at the area under the curve. We picked 2 arbitrary points in time last time, like t initial and t final, on our velocity versus time graph. And I described what it meant to find area under the curve. It means the area between the function, in blue here, and the x-axis. So that would be like this area right here. And we said that finding this area under the curve provides you with the change in position. So area under the curve on velocity versus time graph tells me, this time graph tells me change in position, or in this case, delta x. So this goes back and tells me what the change in position is over here between whatever this initial and final time are. So we'll just review that quickly. That's going to be between here, there's final time up there, and here's our final position. The position's being read off the y-axis. It's the x position is being read off of the y-axis here. So here's be my change in position would be whatever number this change in position is for x final minus x initial. That's going to be some difference, some change in position. That's going to be equivalent to the area under our curve in the velocity versus time graph. Okay, so now we've finally gotten to three types of graphs representing the same scenario: position versus time, velocity versus time, acceleration versus time. Now let's take a look at a slightly different scenario where instead of a constant speed, our car is speeding up, still moving all the way in the positive direction. So here's our new scenario. Alright, I got my graphs labeled. Now I'm talking about a car that's speeding up. It's starting from, let's say, starting from rest at the 0 position. So it's starting at rest at x equals 0, and it's going to speed up at a constant rate. We should have a quadratic or squared function right there for our position versus time graph. Notice, remember, that my slope on the position versus time is the velocity. So my slope starts out, should be at 0, and then it is getting steeper. So that means I am getting a speeding up. It could be steeper like this or steeper like that. It's getting away from 0, either positively or negatively, and that's going to tell me the value of the velocity. Notice also my slopes here are positive. These are positive slopes. So that tells me that the velocity is positive. So velocity is always positive here. That's important. So the steepness tells me the magnitude of the velocity, how fast, and then the positive or negative of the slope tells me what direction the velocity is in, what direction the car or object is traveling. Alright, so I have my quadratic or squared position versus time because we're speeding up at a constant rate from rest, and now my velocity is going to be linear. So there's my linear velocity. We just mentioned that we can now find the slope on the velocity versus time graph to tell us the acceleration. Well, this is going to be easy. The slope is constant on the velocity versus time graph, right? I can pick any 2 points. Boom, boom. Change in y over change in x, or rise over run gets me my slope. So my slope here, my slope on the velocity versus time graph tells me what the acceleration is. Just like slope on position versus time told me the velocity, the slope on the velocity versus time tells me the acceleration. Velocity is increasing at a constant rate. There's our linear trend. And so we have a constant slope, so we have a constant value for the acceleration. So acceleration is going to be a nice flat horizontal 0 slope line right there. The slope on my velocity versus time is a positive slope, therefore my acceleration is a positive value. We will always have a constant or non-changing value for the acceleration in this class, because that's what you do with algebra-based physics. If you have a changing acceleration, you need the calculus. Alright, there are slopes. Slopes take us to the right in these pictures. So slope on position versus time tells me velocity. Slope on velocity versus time tells me acceleration, right? That's taking us to the right visually in where I'm putting these graphs. We can also find the area under the curve. We mentioned that with velocity versus time. What does the area under the curve in velocity versus time tell me? Between 2 points in time, the area under the curve tells me what? Yes, excellent. The change in position goes back the other way. And remember, area under the curve really means the area between the function, that's in blue right now, at the x-axis, which is the time axis. So what do you think happens when we try to find the area under the curve for acceleration versus time? Let's take two arbitrary points. They will correspond with Ti and Tf, or T initial and T final, as drawn on the AvT graph. Looks like I can find an area here. It's going to be a pretty easy area to figure out. It looks going to be a rectangle or a square. What do you think that's going to tell me? Yep. It's going to take me back to the velocity. It's not going to tell me velocity. It's going to tell me delta v, change in velocity. Those area under the curve, those tell you a change in something. So area under the acceleration versus time graph, area under the acceleration versus time graph curve tells me the change in velocity between time initial and time final. Okay, visually on our velocity versus time graph, that would be the difference between these two y value numbers. There's v final, there's v initial. They correspond with t initial and t final. Right, so delta v on my velocity versus time graph would be the length of this portion of the y-axis. So the area under the curve on the acceleration versus time graph takes me back and tells me the change in velocity, v final minus v initial. Remember, delta v, change in velocity, is always going to be delta final thing minus initial thing. All right, that takes us back to the left, this way. All right, we go into the velocity versus time graph and we get the area under the curve. That takes me back to the left and that tells me delta x, which remember delta x final minus x initial, and that's going to be represented on my y-axis on the position versus time graph because the position is on the y-axis. Let's put in those t initial and t final marks. Where are they going to be? Right there. Right there. Corresponds on the y-axis to x initial right there. X, get out of the way, x final, still need a labeled axis. Okay, so the area under the curve on velocity versus time takes me back to the left to delta x, change in position, and that will be actually this distance on the y-axis representing the change in position of the object in the x dimension. So now we've taken a look at two of the major scenarios, moving at a constant speed in one direction and speeding up from 0 in one direction, and we have position versus time, velocity versus time, and acceleration versus time. Things you can always do with graphs, and the first thing you should do at the beginning is like make a title for it or read the title. Look at the axes. How are they labeled? Is it a position versus time graph? Am I looking at the x direction or the y direction on a position versus time graph? Check it. If it's labeled and you're interpreting, look at the title and the labels on the axes first. If you're making your own, title it PVT, VVT, AvT, whatever. You're going to be making all three of them to represent one scenario. Title them properly and then label the axes properly. Time t is always on the x-axis. Position in the horizontal dimension is going to be x, and if we're talking about vertical, that's going to be y. After doing the title and our axes, you can read stuff directly off the y-axis. So if I'm looking at a PVT graph and I want to know the position at a certain period of time, you just got to look right here, like at x final. That's the position at final time. Other than reading stuff off the y-axis directly, we could read stuff directly off of the x-axis. At what time is it at a certain position? So vice versa, you can read stuff off of the axes. And then we said we can look at slope, right? So slope on position versus time takes us to due velocity, and then slope on velocity versus time takes us due all the way to the right to acceleration. So we can use slope, that's something else we can read. And then if we can go the other way, we can look at the area under the curve. So if we start over here on the left with the acceleration versus time, if we find the area under the curve and acceleration versus time, that takes us back and tells us change in velocity. Not velocity, change in velocity between 2 points in time. From velocity, I find the area under the curve. That takes me back to the left once again to not position, but change in position between 2 points in time. All right, so now we've covered finally all three types of graphs. I hope that's been helpful. Go check out the online interactives that deal with interpreting and connecting graphs. They can be very, very helpful. I'll see you guys next time.